Welcome, everybody. Tonight we're working on Unit 10, and the topic for the evening is neural networks. If you remember last week, we were talking about reinforcement learning and how that's used. We never got to the gym stuff by OpenAI. I do hope to kind of go back and maybe record a video on that stuff, but you guys should explore that technology is what I'm going to say. And you can do so with the help of the slides. Our agenda for tonight is to learn about neural networks, what they are, where they came from, how we use them, and then how we see the math that sits behind it, and then how it gets applied to AI, and it's a really important aspect of AI. Terminology wise, and like right on this slide here, you can see right away that often when we talk about neural networks, there's a few different terms we use for it and a few different acronyms. And the first one is that AN one, which is an artificial neural network. And we're doing that through technology. But usually, we'll just say neural network. We don't say artificial neural network, even though that's what it is. Because a real one would be like what's in your brain, right? And the important aspect of this is that's kind of where it comes from, is thinking about how the brain works, how neurons in the brain works, and that was the inspiration for this stuff, which is okay, kind of crazy because now AI kind of thinks, and it's not accidental, by the way, but it is based on mathematical theories and network diagrams, which we're going to learn about. All right, so let's start with just the basics. When we had that first AI course, the previous course, right? We talked very briefly about neural networks, what they are, and then, had like 3 slides on it and then moved on. Okay, so now you're getting the full on barrage of information here. So we're going to look at what they are, where they come from, and what they look like, and what is their structure. All right. So it says here, what are neural networks? And it says they reflect the behavior of the human brain. And so basically we use these to allow computer programs to recognize patterns, solve problems in the field of AI, and of course in the subset of machine learning and deep learning, right? And remember, neural networks are part of machine learning and deep learning, which are subsets of the bigger area of AI. Machine learning, if you guys haven't figured it out yet, it's a really important area to AI because that's how we train our models, and our agents is using machine learning models typically, all of which have basis in mathematics, right? And this is why students in our AI data program have to take more math than most people, right? I'm hoping that you don't fear math so much as a result of this course, but I know some of the equations that we look at do kind of get weird and hairy looking, especially if you've never seen calculus equations before. All right, so the acronyms, that second bullet, neural networks, that's usually what we're going to call them. We also call them artificial neural networks. We also call them simulated neural networks, each with their own acronym, but they're part of machine learning. And they're what really drives the deep learning algorithms that are even a deeper subset of machine learning, right? And the inspiration, of course, comes from trying to mimic what our brains do naturally, right? Which is we have little neurons in our brain, and when we created mathematical models of it, we created this thing called like network diagrams. And by the way, network diagrams are not just used for machine learning. We used, for example, network diagrams to do operations or business analysis kind of stuff too. And it's a really interesting way to solve problems. And you'll see like kind of the interrelation of it all. Well, there is a history that goes with this. And the initial idea kind of goes back to this guy named Warren McCullough and Walter Pitts, and you notice that they came up with what they called a logical calculus of the ideas of imminent in nervous activity. So they were looking at what our nervous system was doing and trying to figure out how it operated and how pathways were formed in the brain to learn information. And in 1958, Rosenblatt came up with the development of the perceptron, which is an important aspect of this. In 74, Paul Werbos was the first person in the US to note its application within neural networks. That would be the perceptron. And then in 1989, Jan LeCun published a paper illustrating how constraints in backpropagation and its integration into the neural network architecture can be used to train algorithms, which is where we're at, right? And we're benefiting from all these predecessors having thought about it. But the concepts aren't new, right? They've been around for a while. They kind of closely mimic the whole development of computer history, right? Which shows you that people have been thinking about this stuff for a long time. The magic of AI didn't just happen. You know, it was a process to get to where we are now. Remember, we just have the technology now that can take advantage of it. Finally, you know, we finally have computers that can do it, you know, rather than just imagine what the computers can do. Neural networks are often represented in the form of these network diagrams. And, you know, and there's layers to this. And you'll notice that, you know, they label them as input layers, right? So the ones on the far left here. And then you have these hidden layers in between. Sometimes there's one layer, two layers, three more, you know, who knows? And then ultimately there's an output layer. And notice how the output layer converges basically to hopefully a solution or one output, right? Like I said, network diagrams like this are used in a lot of capacities. And one like real classic example, when I used to teach like quantitative analysis and operation science, what I would tell my students, right? And I gave you the example of like last week where what does it take to ship a pallet of goods from New York to LA on a truck? You know, how many different roads can you take? Well, you can take any road you want, right? And so there's really more than one pathway, and network diagrams are like that, right? So in other words, you'll notice that from any input node, it's possible to travel to any other node, and all the nodes that lead to the output layer, there's every pathway that's possible is represented, right? And this is very common. So networks are very complicated, right? And for each one of these nodes, you know, that we call them, there's pathways, and all of these have labels and names that go with them, right? We're going to learn all this terminology, but there's input layers, there's hidden layers, and an output layer. And we think of these nodes as the neurons, right? And then there's these pathways that connect them all. Notice the last bullet here, though. The primary job of a neural network is to transform all the inputs we're putting into it into some sort of a meaningful output. When I would teach operation science, we would, you know, for example, you know, this might be like New York, Washington, D.C., and Atlanta, and this is Los Angeles, and I'm shipping products. And then, well, I could drive from New York to St. Louis, from St. Louis to Denver, you know, that kind of thing, right? And then all the pathways had values. And ultimately what we're looking for is what's the best way, what's the cheapest way, or the fastest way, or the safest way, or whatever, right? These are the things that you think about. All right. So each node, so the circles or artificial neuron, connects to another, and it has an associated weight and threshold. So the connection has a value attached to it. So if you travel that connection, there's like we put some sort of a numeric value or formula on it. You know, so for example, if this was like the road from Chicago to St. Louis, there'd be a certain amount of gas you would expend to travel, right? Or if I was going from Chicago to Denver, that would be a different value because it takes more gas, more time, you know, that kind of thing. If the output of any individual node is above the specified threshold value, that node is activated. sending data to the next one. So in other words, just because a pathway is possible doesn't mean we're going to follow it. But if we follow it, then the value of that pathway is utilized. This is really what they're trying to say. So if I was driving from Milwaukee to Madison, I would just probably take I-94 and go straight there. I wouldn't drive up to Appleton first and then drive to Madison. How does that make sense? Right. Unless I want to stop in Appleton to go shopping. Okay, maybe. Right. Not likely though. Right. And this is really kind of the point of it. So anytime we travel a pathway, let's say we travel this pathway and end up here, now I still have 4 possible pathways. I can still hit all the other nodes in the next layer, but I got to figure out which is the one that makes the most sense so that we can have the best output. Right. Right. If we don't follow a path, then the data is not passed along that path. Sometimes we follow paths and sometimes we don't. Your brain works the same way, right? If I have a memory about my kitten, right, those are certain pathways in my brain. It's not the same pathways as the memory of my puppy. You know, some pathways they could have been utilized together. If I had the kitten and the puppy together, maybe I'd use more pathways. I really don't know. But if I don't pass data from this layer to this layer, I can't get to this layer. That's the point, and I can't get to the output. All right, so it says the network can acknowledge and observe every aspect of the data set and how different parts of the data may or may not relate. And so this is kind of one of the interesting aspects of it. So like we can take very complex situations, right? Once again, traveling the country to move efficiently from one side of the country to the other can be very complex, right? Or very simple, right? Finding these pathways when you have a ton of data is complicated. So, but for example, if we stick with the truck example, you know, trucks that carry cargo usually don't go down residential streets. They go down, you know, major numbered highways or county trunk roads or interstates, right? They're usually not going down the parkway, right? In many cases, they're disallowed. So some pathways just don't work in certain networks. And sometimes it is a complicated thing. So sometimes we follow multiple pathways for a neural network. And it can create a more complex situation in the output as well. Notice that they do rely on training data to learn and improve their accuracy over time. So that's important. Let's take a look at each layer. So the outermost layer is the input layer, right, marked in yellow. The neuron basic unit of the neural network, those are the circles. Neurons either send values or receive values, right? So you see the hidden layers both receive and send information, where the input layers only send and the output layers only receive. I mean, it's pretty intuitive by looking at it. Every node is connected with every other node on the next layer. So like if I start here, all 3 of these connect to all of the nodes in the next layer. All of these connect to all of the nodes in the next layer, and all of these connect to that. Whether or not we follow it, the connection's there, but we might not walk the pathway, right? Every time we move over one of the pathways, right, there's a weight assigned to that, and we talked about that. Weights are assigned to a neuron based on its relative importance, right? So I might want to travel through certain nodes and not travel through others, and then there's kind of like a cost of going over the pathway. So where it says when all the node values from the yellow layer are multiplied along with their weight and summarized, it generates a value for the first hidden layer. So in other words, we look at what these are and their weights, and then that gives us a value for why we're going here. Based on that summarized value, the blue layer has a predefined activation function. So that means whether or not the node will be activated and how active it will be depends, right? So for example, use the Milwaukee to Madison thing for example. Now, driving out of my way to go to Appleton, unlikely to happen. It's possible, but unlikely to happen. Taking a detour in Waukesha is probably more likely because that's just a little way off the road, not a whole lot of way off the road, you know? And so those values help to determine. Now, the fact that you can take the values of all those nodes and kind of combine them and summarize them, right? And this is where we get like multiplication and matrix multiplication in the mix again. That summarized value helps us determine those pathways ultimately. That's the point. With the hidden layers, you know, and there could be, you know, once again, one hidden layer, you know, or multiple ones. Ultimately, we don't care what's happening in the hidden layers. Or, well, you know, normal people wouldn't care what's happening in the hidden layers. We want to put in inputs and we want to get an output that's meaningful, right? We call, you know, it says we call them hidden layers because it's always hidden from the external world. People don't necessarily see the data or the logic or the formulas or the pathways in these models. But that's where all the computation takes place. That's where all the determination takes place. Really, what we look at typically is if we do this, what's the result? That's what we're looking for. We don't care about what the million possibilities are to get there. We just want to know what the best one is, right? And that's, if you think about it, that's how AI works. If I ask AI a question, I want the best answer, right? Not, well, there might be other possible answers too. And AIs are known to sometimes not make the best, you know, responses to stuff. Last bullet, you know, it says the hidden layers take all the inputs from the input layer, perform all the calculations, and generate results. And it can be multiple layers, it might not just be one or two. Right. The outer layer or the output layer is so we can just you know, look at the result. And let's face it, folks. Now that you guys know how to code, like in Python, if a user's using your Python program, they don't care what the code means. They might just be saying, okay, like, give me the data, here's the output. They don't care what the logic is in between. And that's how neural networks are too. Once you have them set up, nobody cares what's going on in the middle, right? They just want the result. All right, so that kind of like reinforce that concept over and over again. All right, so like, you know, this would be like kind of like a discussion point if we had like a 4-hour class, you know. So like some questions you could ask, you know, is there a value to this to businesses? And the answer is absolutely yes, by the way. And how are businesses you're using neural networks is a question. All right, so that's something you could research, and there are answers out there about it. And then how do those change how a business operates? All right, and I'll go back to my trucking example because it is very pertinent. Right, if I figured out an efficient way to have a trucking route, wouldn't I want to use that every time? Especially if it saves gas and saves time, right? Yeah, you would, right? If there's a choice, so for example, and here's kind of an interesting example. Okay, so I'll date myself a little bit. These days, you know, if we're traveling somewhere, we often use Google Maps, right? Or like your GPS, if you have one in your car still, and you put in your destination, and it takes you there. You don't question how. And the good GPSs will be like, oh, there's a traffic jam up ahead, rerouting, right? And it takes you around, right? Why is it doing that? Because there's congestion in the network, and that pathway, which was once the most optimal, is now no longer most optimal. And so you follow a different pathway. And so that's a primitive example, but once again, pertinent. Okay, let's take a look at how this stuff works. All right, here's some of the topics we're going to hit here. Let's start with this biological neuron. All right, so a real neuron does have inputs, you know. So this, you could think of this as like the node, right, or the perceptron, if you will. And there are inputs to it. So there's these little like things that come out of them. They're called dendrites that send information into the neuron. The neuron does something to process it. We really don't know what, I mean, well, they kind of probably do, but, and then it outputs, and it might go, through the axon thing to something else. It might control a bodily function, or it might make you speak, or it might make you whatever, or it might send information to the next neuron for processing. That happens in biology too. And there are notes on that if you guys want to read up on it in the notes section of the slides, by the way. All right, so how does an artificial network replace or replicate, it says here, a biological neuron? So the input to a neuron, right, is the dendrite. The neuron is the kind of a hidden layer, and the output is the result of what happens as a result of that processing of the neuron. So like your input might be visually, I don't know, somebody's throwing a baseball at you and it's coming at your face and it's going to hit your face. Your brain processes that and the output is move, right? So that might be how the neuron works. But there are those layers in there, and this is why they kind of modeled it. Like we're throwing inputs, it's being processed, and output. Now, those of you that have had programming with me, do you guys remember when I did that in the Python class? We talked about the basics of programming and IT systems, and all IT systems are built on that exact model. We get inputs to a system, stuff gets processed somehow. We usually don't see what that logic is, but then there's an output. Input, process, output. It happens with neurons. It happens in neural networks, right? That's a pervasive theme in IT. We call it the system model, right? It's also pervasive in other areas like manufacturing, right? And I use that example in my Python class too, where we, like in manufacturing, we have inputs of raw materials, let's say like a tree from the forest, and then we process it and chop it up and mulch it, and we turn it into the output of a piece of paper. So we go from a tree in the forest, process, to a piece of paper, right? And once again, good example. All right, let's look at the different components here. All right, so as we start to look at this, we do have components inside the neural network that are kind of matching the real neurons, and the terminology that goes with it. When we move through the structure of it, you'll notice once again this flow of inputs of information, and here they're just taking x's. These are unknowns. It could be any value or piece of information. There might be one or two or three, or there might be however many. It could be thousands or millions, for that matter, right? Then we place weights upon that information. So as it's traveling over the network, the pathway receives a value. And then we summarize that value. That's the sigma stands for summary of all these different weights and values of inputs. And we come up with basically what we call a net input that goes in, and then we process it, and there'll be certain thresholds. So if we like meet the threshold of that neuron or node, then we might follow that pathway to our output. It's activated and we'll use it, right? Driving down I-94 to Madison from Milwaukee makes sense. Going up to Appleton and then driving down does not, right? And so we would activate the 94 route because all our weights and inputs and data tells us to, right? And there's a certain threshold. All right, so neurons are similar to biological neurons. They are nothing but the activation function, so they have to trigger on, in other words, to be used to do a task, right? So if they're not triggered on, we don't follow that pathway, they're not used. We will have basically a change of state, like if we follow a pathway, we'll use the number one perhaps. If we don't follow it, we might use zero, or we might say -1 if we don't follow it, or +1 if we do, right? And why do we assign numeric values? Because we can process numbers. Computers process numbers, right? And that's what they like to work with. So that's why we assign values to things, because then we can program them mathematically with math models and computer programs to execute and do it logically. It says here the sigmoid function is commonly used activation function in an artificial network, by the way. If you want to look up the sigmoid function, they do have a link on the notes page here, and I'm just going to drop it into YouTube here just very quickly. I apologize for the ad.
In today's video, I want to talk about the sigmoid function. The sigmoid function plays an important role in the context of logistic regression. What do we mean by that? Logistic regression is a technique to predict the outcome of binary classification problems. In this case, the sigmoid function plays the role of an activation function. It takes the weighted sum of the input features as an input and outputs the probability value of the outcome. Let us see the graphical representation of the sigmoid function. The sigmoid function, as we can see, is an S-shaped curve. For any value of x, the sigmoid function will output a value between 0 and 1. How does the formula of the sigmoid function look like?
All right, and I want to actually, this for me is the important parts. This is why I'm focusing on this. And the point is, in order for this to trigger, there's going to be a threshold point, and that's going to be predetermined by your data or your scenario, right? But basically, when the value is 0, so when we're at the bottom end of this graph, and I can get rid of the closed captioning here so we can see it, it's not triggering. And then we're assuming when it reaches whatever this value is, it might be halfway up, it might be more, it might be less. And it gets past that point, then it triggers, and then we're following the pathway. And here they're using 0 and 1 as the values, but notice in the slide where we talked about -1, +1, but the shape of it when you plot it. So when they say a sigmoid function, it's an S-shaped curve like this. That's what they mean, right? So I'm just trying to demystify the terminology. It's nothing really complicated, by the way. Right. Back to the PowerPoint. All right, it says here the biological neuron is connected in hierarchical networks, and with the output of some neurons being the input to others. We mentioned that already. And they're represented, the biological ones, as a connected layer of nodes. Okay, so this is where we borrow it from, and we borrow it from nature, right? Because nature's already done this. Nature already figured it out. We're just trying to copy what nature is doing. So each node takes multiple weighted inputs, applies it to the neuron, to the summation of these inputs, and generates an output. So it does a combination. And I know I'm saying this over and over again, but it's to kind of clarify it, hopefully, for you. Another aspect of working with neural networks is bias, right? And so we look at the standard equation for a linear equation, right? Y being where it intercepts the y-intercept. This is the constant. That's the intercept point. And then there's a slope indicated here as well. But basically what we're saying is we try to predict a value of y. That's our output based on the input of x. And then M and C are the weighted values, right? C is considered the constant or the bias, how much, it's going to change the output, and that's always going to be there. And then M is dependent on how strong the value is, right, to make it trigger or not. It says bias helps the model in such a manner that it can be a best fit for the given data. And we say bias gives freedom to perform best. Okay. And that's not bias in the other way that we're thinking about. This is bias numerically, by the way. All right. So a little bit of a kind of an example here. And they're using the example of like a voice assistant, like Siri or Google Assistant or Alexa or something like that. And it says when you they listen to your voice, for example, and I say, "What is the time?" Right? It has to break down and understand that there's 4 different words being spoken. So hopefully you said them clearly. And then each word in and of itself has its own pattern, which also needs to be broken down. But you'll notice there's 4 words. So we kind of have 4 inputs, and those will get processed, and then it'll break it down and give us certain outputs. And it says, so each word comes in as a pattern of sound, and the sentence gets sampled into discrete sound waves. So it really, a voice assistant has that capability to recognize that different words are being spoken and to break them into their waveform, right? And I think we can kind of continue with this. And okay, well, if I say the word "what," it also has to break down the letters of the word. So so I broke down the word, and now I'm breaking down the letters. Interesting, right? So in a word like "what's" an interesting word, because you really hear the H. Yeah, it's kind of one of those things, right? English language is kind of like that, where letters don't necessarily always get sounded out, right? That's a bane to a lot of people trying to learn English. And English, unfortunately, is one of those languages that's such an amalgamation of so many other languages put together that kind of happens, right? So we incorporate a lot of different approaches. But if you learn like a language like Spanish or Greek or Latin or something like that, every letter has a certain sound, and it's just always the way that sound is, right? Now, okay, so we split apart the words. Now we're splitting apart the letters into smaller pieces. All right. And then we can look at the individual letter sound and determine that, and notice like a sound wave kind of does look like that. It's a waveform, and it has fluctuations and nuances and frequencies in it. And we can break that apart in what to call different amplitudes. So the bigger the line, the louder it is. And think of how you say W, or when I say the word "what," it kind of does kind of start out quiet and gets louder, right? And trying to emphasize it. And they're looking at all the different waveforms within it and giving them values. They're giving, okay, so W has all these amplitudes of volume for that sound. And so we're giving those values based upon that. It doesn't come from nowhere. It comes from somewhere. It comes from physical reality, basically. And so then all of those become pathways to the input layers with weights upon them, right? So we collect the values at intervals, form an array, right, or a list or whatever. Different amplitudes come in for different letters, and we feed the array of amplitudes into the input layer, right? So I guess we said all that. All right. Then it says random weights get assigned to each interconnection between the input and the hidden layers. In other words, allowing each one of these neurons to interact with the hidden layers and every possible pathway route that could be followed, whether or not it makes sense. The possibility is there, right? It doesn't make sense to go to Appleton and go to Madison, but you could if you had to. So the random weights get assigned to each connection between input and hidden layers. So anywhere there's connections beyond the input layer, like all these pathways will have weighting attached to them. We often start with a random key, right? 42 or something, like one of those kind of numbers. Um, and it says, as assigning a present value to the weights takes a significant amount of time when training the model. So this is why we use randomness in the process. If you were to get the actual values, you would get a better model, but then it takes a lot longer to train it because I got to like follow every pathway, tell you what the value is, and then see if it's a good path to follow. In an ideal world, that's what you would do. You would work off of real data, but sometimes we don't have that to work with, right? And that's an issue we'll talk about as we move forward. The weights then all get multiplied with the inputs, and a bias is added to form the transfer function. And the transfer function looks like this, right? It's basically saying we summarize all these values, we take all the weights, combine them all, and we do that, and we come up with a sum, one singular value that represents the whole thing as a transfer function. The weights are assigned between all the interconnection points, right? We said that. The output of the transfer function is fed as an input to the activation function. So as we're feeding stuff in, if we can trip that sigmoid function into the range we want to follow that pathway, that's the activation function, right? So the output from one layer going to the next layer, so the output becomes the input to the next layer. How many layers are in between? We really don't know. Some have very few layers, some have very many, and very many nodes. These are indeterminate things. It is situationally based, depends on your network, right? And I use the example of the roadways again. Roadways going from across the country, there's many, right? Maybe they don't all make sense, but in some cases they do. All right, so they're going to kind of keep going here on this example. All right, so they say the acoustic model contains a statistical representation of each distinct sound that a word makes. So in order to do voice recognition, the first thing they do is they have to train the computer to listen to how we speak and be able to take the words we say and figure out what letters we're speaking. So we build these models. And how do you do that? And has anybody here ever used a voice dictation system? Yeah, this doesn't happen so much anymore. Who said that?
I did.
And Finley,
I have used those. They are horrible for the purpose of taking Dungeons and Dragons notes because they do not do fantasy names. They do not even do obscure English words. You
yeah,
have to be talking either legalese or layman, full stop, or it will not understand you.
yeah, and that's a good way to say it. And I know, like the very first time I encountered dictation software, and this is a long time ago, mind you, I was like in college at the time, and we got Dragon Dictate in the computer lab, and I'm like, oh, this is cool. I can type my paper by just talking, right? Silly me, right? Because I didn't want to type it all. And so what I did is I used the software, but then I realized, oh, I can't just use it. I have to train it first. So it would give me a paragraph of text to speak, and it would have me read it in, and it would analyze it. And then it would give me more text, and it would analyze it. And whenever it would have problems with certain words or ways I would speak, because everybody has quirks in their voice, it would like hammer that, like, say tomorrow again, please, And then it would, after a while, and the more you used it, right? And in the old days, it learns to exactly, it learns to understand you, right? As opposed to somebody else. Now, these days, we use the stuff on our phones, and it really doesn't require a lot of training, but there are still models like that you do train, and the ones you train work better, by the way, than the ones you don't. So the point is, we can train them. Once we train them, then we basically have a lexicon, right? So the lexicon contains data for every different pronunciations of every word. Like, for example, I could say, what, or what, right? Or what, or whatever, you can say it like 54 different way, or you can be like snarky and go, what's up, or whatever. Okay. I don't know how you read that one, but that one probably comes in as WASSUP or something, right? Which isn't a word. So then you would have to say it again. Right. So ultimately, they notice how they put in the acoustic model and the lexicon, and basically we can start to build a language model. So first we're breaking apart the words, then we're breaking apart the letters, then we're starting to understand the different ways the words can be spoken and put together and the letter sounds that they make. And then ultimately we actually build a little library that it can draw from. So when I'm talking to my phone and it understands me, it's not by accident. It's because of a significant amount of training, and assuming that we all communicate in a reasonably similar way, you might not need to train it. This is kind of an interesting thought. But ultimately, if you speak a letter, it should be able to understand what letter that is based on previous patterns and identify it as such, right? And then this is going to happen for like every word in the dictionary, every letter in the alphabet, every language on earth, right? I mean, like, think about that, right? So you get like these voice interpreters, and you know what, this is really funny, but I forget where I was shopping somewhere, and there were some tourists, and somewhere, from Asia or somewhere, and they wanted to ask for something, and they were asking for it in English, but the person getting the message wasn't understanding, so they did a Google Translate on their phone in their native language, and then the phone's like, where is the bathroom? That kind of goofy thing. And okay, so it works for other languages too. Now, this is really kind of bizarre to think about, because every language you're training it on, you're adding complexity. All right. If you guys haven't figured out, this is kind of a big part of like feeding into generative AI, right? And as we learn this AI stuff, we learn about like generalized AI, then machine learning, then deep learning and neural networks, and then we get to natural language processing, and then computer vision, each being a smaller subset of the greater whole and requiring deeper math, bigger models, more complicated systems to make that all work. So the fact that we're at the point now where we can fire up an AI on our machine or our phone or whatever and generate an image or create computer code or whatever should be a very astounding thing here. But here's a problem. When you're training an AI from scratch, we have this challenge of basically we don't necessarily have enough data to train it with, right? So like, notice it says in specialized domain, traditional techniques frequently struggle to find enough data for training. So why did Dragon Dictate have me read text? Because that's how it was generating its data to recognize my voice. Right? Right. The performance and generalizability of the neural networks may be constrained by the scarcity. So like, if we don't have data to give it, how is the model ever going to get good? How is the AI ever going to really succeed? So one of the reasons why it's taken so long to get to this generative AI state that we're finally exploding right now is because the computing power did increase and the bandwidth increased, and we have more data centers and we have better algorithms, and they've been trained for a long period of time. I mean, how long has Siri been around? Right? Yeah. Right. So we have like a decade or two of data that we've been building off of from all around the world, all the languages, to build these models and train them better. And what's kind of interesting and why generative AI is in the mix here is because it can help us in this regard, and this is why there's a little bit of an explosion in these technologies too, because we're looking for real world data, but maybe hard to come by or expensive to procure or difficult to gather. And so we can use generative AI to create, like what they're doing here, is synthetic images, right? So there's real images, and then there's synthetic images, and then we can use the synthetic images to add to the data sets that we have, and therefore improve the model basically because we're giving it more data to train with, even if some of the data is synthetic. This is kind of interesting. And why does that work? Because we're exploring all the pathways of the network, right? Doesn't mean we follow them all, but we have to explore all the pathways of the network. So, and that really helps these models quite a bit, right? And this is part of the acceleration process. Like once they figured out, it's like, well, hey, we have to get data to train our models, but we don't have enough data. Hey, we could generate data. Okay. And now we can accelerate the model building. Yeah, that's huge. Another thing that's kind of interesting with this is this whole concept of outlier detection and removal. So in other words, if we have a data set, most of the data fits neatly in this area, but then we have that one that's way out here that doesn't really quite fit, right? And what they're telling us here is that outlier data can bias the network predictions, right? So it says, imagine client transaction data. This data trains a generative AI model of normal consumer behavior patterns and distributions. We synthesize samples with the learned generative models, and these simulated samples reflect the data distribution learned. So in other words, the synthetic data can help to rectify this issue, right? By giving us a large volume of synthetic data that maybe helps to eliminate the outliers as a process, because we're working with stuff that fits in the model better, right? So this is, and I want you to think about how this is different from like the reinforcement learning thing, right? Here we're trying to, okay, well, you know what? Let's just get rid of that one. Well, in fact, let's generate some synthetic data that sits neatly in there and do a whole bunch of it. And then that'll be our training model. And then that neural network will be valid for that, right? We're not worried about that outlier stuff. All right, so comparing real data to produce samples can reveal data points that deviate significantly from the taught distribution. So in other words, we can identify those potential outliers as part of the process. And they use basically statistics and probability once again to help us figure out whether something is normal or abnormal. If you get a whole bunch of outliers, maybe that's actually normal and we need to revise our model. If you get one every once in a while, there's one way over there. Okay, well, that's just a fluke, right? So it helps us to, via probability, say, well, that only happens 1% of the time. So it's probably not something we should worry about. If it happened 40% of the time, I'd bring an umbrella. It's kind of a way to think about it. So using relevant and representative input helps the neural network generalize and forecast better. So, and this is what I'm saying. Does it all fit in there? Let's get a bunch of stuff that fits in there, and then that outlier stuff will be kind of cast off. Okay. There's also this data balancing concept. So, and this is kind of interesting. It says in many data sets, there's a problem known as class imbalance, where some classes have fewer samples than others. So for example, if I want to see how a snowplow performs, I probably have lots of data for when there's like 2 inches or 6 inches or 4 inches of snow, but I probably don't have a lot of data for when there's 20 inches of snow, unless I live in like Alaska or something, right? Because most of the time it snows around here, you get 4, 5, 6 inches, and that's kind of it, or an inch or two, and that's kind of it. So, so sometimes we don't have enough data in those ranges to kind of rectify that. So generative AI can be used in those situations to create data for the data sets that are lacking, so that we do deal with that kind of data, we know what to expect, and that we do have good pathways to follow. So, hey, we don't have a lot of 20-inch snowfalls. Let's generate some simulated 20-inch snowfalls so that we can see how the snowplow performs, right? And, will it break the plow faster? Does it need more service? That kind of thing. And so therefore, if we can create balanced sets of data, then all those pathways in the network are more fully vetted to see if they're the correct pathways, right? Because we've tried them a bunch of times to know they're not the right ones or the correct ones or whatever, right? All right. So another one that's kind of a thing too is like the privacy concerns. So like what we mean is, like when we're using AI against personal information, we don't necessarily want to really use people's real information in order to train a model. So we don't want to put that at risk for the sake of training a model. This is a concern, right? And a big one. Um, and I know we talked about many of these issues, but generative AI, it says, gives us ways to basically have synthetic data like simulated humans where we're not exposing people's personal details, and then we can train the models without revealing any sensitive information about anyone, right? And banking that in some database or something. And they have different techniques they use too. So they say like differential privacy can be incorporated into these models to ensure data protection. So we can orchestrate things so that we aren't compromising people's information. I do think you guys should be aware, though, that people do exactly the opposite of this out in the world these days. For example, on social media, right? Like, I don't know how many of you have played with the Meta AI, and I've been meaning to kind of like tinker with it a little bit, but I and really don't want to expose my personal data or my personal opinions on it. But I would be interested to hear like if you guys have had anything interesting happen on there. But like in a social network like that, I mean, they have a ton of your personal information and location history and preferences and likes and dislikes and loves and who you're connected to and who your friends are and where you went to school and your phone number and yada yada yada, right? And what are they doing? They're training their models with your real data. So your data is exposed, right? So think about that when you're using on platforms like that. Like, what are you sharing? What information are you providing? Do you want to provide it? Some people don't care. Some people care a lot, right? You should be knowledgeable enough to control it. Is my point. All right. All right, we're going to go into this, but we are going to take a 5-minute break here. We're already an hour in, so I'm going to pause the recording, and we will resume in about 5 minutes. It is now 8:50, so back at 8:55. Okay, folks, we're back from break, and we're going to move on in the slideshow here. We're going to look at some of the algorithms that sit behind this stuff, and we're also going to look at what a learning problem is, I guess. It says in a neural network, the learning process is basically initiated by dividing the data into 3 different categories, right? So we'll have a set of training data. And it says that it allows the network to understand the weights between the nodes so that we can traverse all the pathways and stuff. That will also have a validation set, and then we'll have a test data set as well to see if we have a good, rate of error, basically. So sort of like other models, but notice we have that validation thing, which is basically the fine tuning aspect of it. We do use, other algorithms in the mix here too, but one of the main things that we try to do with any type of network problem, by the way, is what we call optimization, right? We're trying to find the optimal way through based on whatever criteria we're trying to solve for. And so when we come up with an algorithm that works, we call this the optimizer, of the network. There's different aspects to these, right? And they all have their own characteristics, as it says. So there's different algorithms we can use, and each of them have different memory requirements. Some of them have different levels of numerical precision, which may or may not be important. And some of them are faster than others, which may or may not be important. It just really depends on what you're trying to achieve. And that you basically tailor it to the issue that you're dealing with. All right, so to define what the learning problem is, it's usually, and notice I want you to think about like optimization here. So like, for example, if I was optimizing my travel route to Madison, what are we really optimizing? my travel time, my fuel cost, that, or maybe the ease of driving or something, there's values we can place on that. So that very first bullet, when we're doing this, we're usually looking to minimize some sort of a loss. We want to make the most optimal path, meaning we want to lose the least amount of time or lose the least amount of fuel, that kind of thing. So this is all done in the form of functions, right? And so we look at basically this thing called the loss index, where we're looking at how much value we're losing by taking a certain path, right? And that's going to be evaluated. We're gonna sit and measure that. We go into a process of regularization, right? So it prevents overfitting and over controlling basically the complexity of the network. But ultimately, the goal is, right, to minimize that loss index. And I apologize, I'm trying to find my other slideshow screen here. Oh, there it is, because I sometimes use the notes on those. We also have to look at the definition of some of the things that they use in the formulas here. This is very superficial, mind you, but we have basically the loss function represented as a function of W, and it depends on adaptive parameters, so weights and biases, the values going over the network and the biases in the formula. We group those into vectors, basically single dimensional vectors that we call W. And then we try to minimize, the loss function. So we try to minimize the loss of the value of a function via these formulas. We can calculate at every step along the way. That's the other point here. And that's something we will be doing, with code, of course. We look at basically groupings of derivatives, and we start first with the gradient vector. We'll talk about that more as we move forward. In the second level, or the second derivatives, we're looking at what we call a Hessian matrix, which is a combination of values once again. And I don't know if you guys are picking up on this, but we're often taking all the pathways possible and summarizing them, usually by multiplying and adding, coming up with singular values that we can use for comparison. We talked about how we can take complex matrices and multiply them and come up with smaller matrices or vectors that have values that we can use for the basis of comparison. And because all that information we fed into it are, factors in that value, it works, right? Because it affects the value in a summative way, and that's kind of what they're pointing at here. There's a bunch of different algorithms that we can use here, right? And they fall into two general categories. One is the one-dimensional optimization, and then we also have multi-dimensional optimization. They talk here about how the loss function depends on multiple parameters, and the single dimensional or the one-dimensional optimization is very key in neural networks. So usually linear equations is basically what we're talking about here. There's a couple of really popular ones, the golden section method and Brent's method. We also have the multi-dimensional ones to consider. And in these, basically the network's trained by choosing something random that we throw in. And we were just talking about this a little while ago, often generated by either random number generators or synthetic data, that kind of thing. And then every time we iterate the code, we try to decrease the loss function. I don't know if this sounds a little bit like reinforcement learning, right? Where you're changing, that value and dropping it each time. So eventually we stop the training. So ultimately we look at how much we're losing, and we measure that. And then we keep changing that, that parameter basically with every iteration, so that becomes less of a factor, and then hopefully leading to a solution. Three common algorithms are the gradient descent, Newton's method, and the conjugate gradient. And yes, we're going to look at each one of these very quickly, mind you. So in one-dimensional optimization, it says that we depend on multiple parameters, and these are very, very important, right? So I mentioned that this is one of the more important approaches. We start by first having kind of like a direction in mind. So like, for example, if I'm driving from New York to LA, I'm not going to drive east, right? I might drive south a little bit, I might drive north a little bit, but generally I'm traveling west. So we're gonna force a direction to start with, because we know generally we need to go that way, right? So this is kind of the point of that second bullet. And we are trying to, once again, minimize the value of the function and using one of the algorithms that we talked about. When we're using the golden section method, we're often using a function that has a single variable, so like maybe a single input, single x that we're solving for, and we're looking to find, in this case, the minimum between a couple of values, right? And so if you look at like these functions, there's like one in red and one in blue, and you run it from one value to another. We don't know what x0 and x2 are. It could be anything, right? But we run it, and as we're running it, at some point we find a minimum value of the curve, and that's really where the optimal solution is. However, right, and this is where it gets a little weird, we don't necessarily have that pathway, so we got to choose the pathway that's kind of close to it. So for example, here, on this line, this seems to be an obvious point for that function, the blue function, right? That's a minimum point. It might not be the lowest point, but it's close, right? Where with the red line, well, 0 is certainly not the minimum, and neither is x1. It's kind of somewhere in between. So now what do you do in that situation? Well, ideally you would break down the pathway, but if I had to pick one point over the other, which one would you pick? Well, x1, right, is the pathway. It's maybe not the direct route to Madison. It might be Highway 18, right? You're going a little out of the way, but it's still pretty direct. And so this is what they're trying to walk through here, and they're kind of trying to explain it in more mathematical terms, but they're showing you that, that when you're looking at these methods, right, this is the golden section method now, that you can look at the intervals between these, right, and you can find, and it says, look at the first bullet, to find out minimum, let's consider x3 is between x1 and x2, right? So it should give us, certain outcomes is what they're saying. And notice on the one function how x3 is way up here, but on the blue function, it's way down here. So but does it make sense for it numerically? We don't know what this value is, but doesn't mean they have to be sequential either, right? And this is kind of the grand point of it. If you read the bullets, the minimum is inside the interval x3 minus x0, right? So in between x3 and x0 is the minimum, right? And so then we look at 3 different points, right? x0, x1, and x3, and it says x2 is replaced by x3. So we're kind of eliminating the x2 in the process here. And so what they're really trying to show you is how the algorithm works logically. And once again, I say don't get super stressed about the math or the logic of this. Let the code do the work and get you there. The point is that sometimes the minimums are obvious, sometimes they're approximations, and there's better answers than others. And I like the x1 and x0 thing is probably the clearest one. Then you have Brent's method, and that has basically a root finding algorithm, and it combines root bracketing, bisection, secant, and inverse quadratic interpolation. Got that? It's like all these complicated formulas, but it still kind of breaks down to basically bisecting things typically. So in other words, if we aren't finding something in that exact spot, we can maybe break it down further. And there's a formula for doing that. Right. And then they start to talk about this multi-dimensional approach. In this one, they talk about the gradient descent. And notice how they kind of flag this one as maybe the simplest of all the training algorithms. Even though it's multi-dimensional, it relies on information that we already have on hand. So from the gradient vector as a first order method. The formula looks a little hairy, but basically we have a starting point. So whatever, variables, W0 is, and then we keep progressing. And every time we progress, we are moving in a direction and changing the values. And basically the rate at which we change those values is what the training rate is. So if we're like incrementing, by 1 each time or 10 each time, that will be the training rate. At some point, every time we're training, we're looking at how much we're losing. Are we reaching a minimum? And then we look at adjusting it so that when we keep iterating and repeating, it gets more and more accurate as it goes. Once again, a little bit like reinforcement learning conceptually. We also have what we call Newton's method, very similar, right? Like the chart looks identical, but it uses a Hessian matrix. So we're doing, remember that means we are multiplying and adding together values from a table or multiple tables together. And it uses basically a different mathematical formula, basically the value of the second derivatives, which helps to get that loss function a little bit more under control. But the same principle, we keep iterating, trying to evaluate how much we're losing or gaining and finding the most optimal value until we reach some threshold that we're crossing. And this is kind of a weird slide because this one here really talks about how we go through the calculation process, right? Once again, I wouldn't worry about you guys memorizing how to do this. If I was cruel, I would try to teach you the math behind it and have you do formulas, and you all would probably horribly fail. So we just look at it on the high level once again, but we are looking at trying to reach that optimal value. And notice that when we put in our first value or like basically the 0, we're still looking for that, basically the minimum with each step. And each time that we go through it, we're recalculating. And they call this the Newton step, and I'm not really sure where they get the name from, probably from the guy that invented it. The other one is the conjugate gradient. And you notice this falls somewhere, it says in between those two previous ones that we looked at. They call it an intermediate algorithm. And notice what it says. It aims to accelerate the slow convergence factor of the gradient descent method. So in other words, the gradient one is an easy one to apply, but it takes a while. So this one tries to balance the two approaches and give you kind of the best of both worlds, like easy to apply, but also converge a little bit faster. It says it eliminates the need for information requirements concerning the evaluation, storage, and version of the matrix. So it saves us, processing steps, basically. Notice it delivers faster convergence in the gradient descent directions. The models are still, at least visually the same. All right, let's talk about some of the different types of neural networks now. And we're going to start talking a little bit more about deep learning and some of the frameworks that go with that. And notice it says deep learning focuses on 5 core neural networks. And yes, we're going to go through them one by one. So neural networks, it says, can be classified into different types for different purposes. And notice we have perceptrons, feed-forward neural networks, multi-layer perceptrons, convolution neural networks, and recurrent neural networks. I don't know if you guys remember talking about any of these in that first course, but we did kind of brush upon these topics. Notice that the graphic over there includes those 5 key ones and some additional ones as well. All right, it's looking at the perceptron approach. And this is the one that guy came up with in 58. One single neuron and possibly multiple inputs. We don't know how many. In this example, there's 2. There's only one single layer. And this particular one is a binary classifier and part of supervised learning. So if it's a binary classifier, what are the possible outputs? Well, true or false, 1 or 0, or +1, -1, something like that. This one was really an attempt to kind of model a basic real neuron. And this is what we call a perceptron. So that's like an individual node, basically, model. So this is a perceptron network. This is the equation for it. Right. We also have the feed forward neural networks. So we have a bunch of different inputs. You notice here we got 4, in this case, 4 in thing. And then we have a bunch of different neurons as well, in this case, 4. But we go from the input right to the output, right? And there's an input. The data only travels one direction, forward, right? That's why they call it feed forward. It goes through the input nodes and exits from the output nodes. There's nothing hidden. It doesn't have to have a hidden layer because they're not, all the pathways are already represented. But notice, not a singular output, right? Last bullet perplexes me a little bit, where it says that these might have a single layer also. I'm not really sure what that implies, that the input is also the output. I'm frankly confused by that comment. But notice this one does eliminate the hidden layers in between. You can go from the inputs right to the output. So like the mathematical conversion happens along the pathways. It says here it has a front propagate wave, right, by using the activation function. So we're basically looking at the input values, seeing if they meet the threshold, and if they meet the threshold, then we have the output. We're using that function. And so notice all the other neural network types use what they call back propagation, but this one can't, right? So the sum of the product's input and weight are calculated and fed to the output directly. What's interesting about this one is this is the kind of neural network that drives facial recognition and computer vision, right? Which seems to me counterintuitive, in first learning it. But yeah, that is behind those technologies. So basically the point of it is that, like, when you're unlocking your phone with your face, that input goes right to the output and unlocks the phone. There's no hidden layer trying to go, is that really him? It's either going to trigger on or off. And or like a fingerprint reader is a good example too, where like if I put my finger on my phone and unlock it, great, it works. But then if I'm washing dishes for half an hour and my hands are all wet and my fingerprints are a little messed up, it might not work. Right? It's a yes or no, right? And there's no formula that's going to change that. Then we get into the multi-layer perceptrons, and this usually has 3 or more layers. So meaning at least one hidden layer is what that means, right? It says data cannot be separated linearly and it's classified with the help of this network. It's fully connected network. That means every single node is connected with all other nodes that are in the next layer. And I mean, that's been all the diagrams that we've been looking at so far are basically that. It says a nonlinear activation function is used in multi-layer perceptron. So nonlinear means it probably has square roots and powers and that kind of thing in the formula to trigger it. The input and output layers are connected as a direct graph, right? So you can see the inputs coming in and going out. This is used for deep learning. It does use back propagation for training the network. And its big usage is speech recognition and machine translation technology. So like kind of like the voice assistants that we've been talking about. And if you remember, the graphics that we were looking at were these networks. But yeah, those are the big uses. Interesting. Then we have what we call convolution neural networks, kind of like feed forward networks, right? These are, it says, utilized for image recognition, pattern recognition, and or computer vision. So it's used in all those areas. They use the principles from linear algebra, particularly matrix multiplication, to identify patterns within an image. And I think that's pretty interesting that is a thing. So like, for example, if you look at the graphic there, there's an image of a car and they're kind of running it through the network. They're telling you which techniques they're using, convolution plus ReLU, pooling, convolution plus ReLU, pooling. And what they're really doing is they're more and more summarizing the data until it gets smaller and smaller, and then they can feed it into the classification system and then come up with, you know, what it is, right? Matching data from before. Right. Then we have our RNNs, or recurrent neural networks. And what's interesting about these, and you can tell right from the diagram immediately, that this network is not forward only, but also can loop back. Okay. A highway example. Well, I can drive out to Madison, but on the way I stopped in Waukesha, and I'm like, oh no, I left my wallet at home, and I drive back home, get my wallet, and then drive back out, and then I get to I don't know, Johnson Creek, and go, oh my god, I need to stop for a sandwich. So I get off the road and I stop for a sandwich, and I'm like, oh, you know what? This sandwich is horrible. I'm going back to Lake Mills. So I'm going backwards, you know, so you can drive backwards on this network. And the point of it is there's a feedback mechanism here, that like you can go back and hit the same layer again. It says the first layer is formed in the same way as a FNN network, and in the subsequent, the recurrent network process begins. So like you start the same way, feed forward, but then you get to the hidden layers, and those could feedback or loop. And it says this is famous for its primary and most important feature, the hidden state. And yeah, and the hidden, and if you look in the notes here, it says, why is the hidden state important? Hidden state remembers information about a sequence, so it doesn't lose the information as you're presenting it or as you're feeding it in. So now we're pulling this all into deep learning, right? And basically it says here, deep learning is basically an interface, a library or a tool which allows us to build deep learning models more easily and quickly without getting into the details of the underlying algorithms, right? And that's really what we want. We want to utilize these at a high level. So it says the key features of a good deep learning framework. They're optimized for performance, so somebody's figured out how to make them run most efficiently. They're not hard to understand and code. There's a lot of support out there. The processes can be run parallel to reduce computations. And what that means from a computing standpoint is I can, if the problem is big enough, like I'm building a model or something, I can have multiple computer systems process it at the same time instead of doing it on one machine. And it automatically computes the gradients. Now, notice they have here a bunch of different libraries listed on the screen, some of which, well, we haven't really used any of these yet, but we may have talked about some of these. And you'll notice that there's TensorFlow and Keras and Theano and Caffe and Caffe2 and PyTorch and Torch and CNTK and Gluon and MXNet. And then they also have the companies listed here because some of these companies use different deep learning algorithms to process information. But these are some of the more popular ones with, you know, arguably maybe the most popular ones are like TensorFlow, Keras, PyTorch, Gluon, right? And some of these names you've probably heard already, but these are all basically big Python libraries. Some rely on others. Very typical. All right, so deep learning frameworks, this is the importance of them. The growth of machine learning and AI has enabled organizations to have smart solutions and predictive personalization to their customers. So it is not a mistake when you log into your social media or your favorite news site and you log in that they present you certain types of information or certain ads or certain things on your feed, because they watch you and they keep data on you and they know what you like and what you click on. And that's all done through deep learning, right? It's not an accident, right? And it's highly targeted, actually. It says not all organizations can implement machine learning and AI for their processes due to a bunch of different reasons. This is where it gets deep. So like the process of like, all right, you have all the data, but you still have to process it and train your models. And you have to basically keep doing that process, because the thing about how like we behave online, if you're being monitored online and they're running deep learning algorithms on you, the more you interact online, the more data they're going to have and the better it's going to get over time. Some companies don't have either the technology, the data processing capabilities, or let's face it, the concern to do it, right? Where other companies do, right? But the point is that over time, these algorithms will give you information that is better and better and better, and really much more tailored to you. So the stuff that you do online, the stuff that you search for online, and we'll just use like, the social media thing, that will keep deepening the kind of stuff you get on your feed. All right, let's take a look at some of these frameworks now, because ultimately we're going to be starting to utilize these with code and stuff. TensorFlow is a big one, and arguably one of the more important ones. It comes from Google. It works with Python and R, right? Those are the two of the languages we teach in the AI data analytics program. And notice it uses data flow graphs to process the data. And so this is kind of like it's kind of like a form of tabular data, but it's a different data structure. And we even have like graph databases and different query languages than SQL to traverse it, like GraphQL, for example. And it says this is really important because as you build these neural networks, you can look at how the data flows through the neural network. So you can visualize it and see how it's flowing through, like which pathways are followed, why do we have this output? You can see where it's going. It says the models are easy to build and can be used for robust machine learning production and allow powerful experimentation for research. And I don't know if you guys recall in the previous course how we tinkered a little bit with some machine learning stuff, very superficially, but we tinkered with it. And you can set up models, and I don't know if you guys remember, you could change parameters and it would change the outputs based on like how you were tweaking the parameters. And a lot of it is web-based, so you can do it in a browser, which is really cool, right? Part of the reason for that is because it's written with Python and you can use that as a back-end language for websites. Bunch of things that go into this. Two really key ones are what we call the tensor board, which this helps build visualizations, right, and data flow graphs. And then TensorFlow itself, which basically allows for really rapid application of different algorithms and just trying things out, right? And if you guys remember that little machine learning thing we did, it was really easy to tweak it and see it change in real time on the screen. It was pretty neat. One reason people like this a lot, it has a lot of pre-written code for some of the most complex things it does. So you don't have to build it from scratch. It's already there. It's just kind of like which tool you're pulling out of the toolbox to use. But it does use recurrent and convolutional neural networks pretty heavily. So feedback mechanisms, for example. Um, it's super flexible, right? And I think we learned that from our previous experimentation. And because it is resource intensive, if you train really large models with this kind of stuff, you have to have a lot of processing power, which is often why we do it out in the cloud or on the web, because a lot of times our local machines can't handle it. We use big, powerful servers out in the cloud somewhere, and usually the ones that are free. But you can get into environments online where you pay for these services, and they're not cheap, by the way. So what do we use TensorFlow for? Text-based language detection, summarizing text. Like when you ask a Gen AI to summarize your readings, so you don't have to read the whole book. That comes from TensorFlow. We use it for image recognition and face and object recognition. We also use it for sounds, time series analysis, and video analysis, right? Like, has that video been altered? That kind of thing. So TensorFlow, very important. Then we have Keras, and that's how I say it. I'm not sure if that's correct. And this was an open source project, by the way. And of course, when we talk about open source software and open source code, that means the people that developed it aren't hiding how they developed it from the world. They're sharing it with the world. And what's neat about that is when people do open source coding and they share it with the world, they get other coders that jump in and go, oh, that's really great, but I can help you fix it or make it better. And they do, right? And they ramp up the capabilities really, really fast. So that's why this one developed so quickly. It says it's a high level API written in Python, as many of these are. And notice it requires TensorFlow and 2 other libraries to work. So you have to have TensorFlow, Theano, and CMTK, and then you run Keras on top of it. A lot of companies use this, but notice some of the big players. I mean, NASA uses this, Netflix uses this, CERN. You guys know what CERN does. CERN is the ones that have that mile-long particle accelerator over in Europe, and they're trying to make like mini black holes and stuff like that. So a lot of big companies use it, and a lot of people, when they're delving into AI, use a lot of these libraries to build their AI, right? And that's why some of these things are pretty profound. So these are some of the key libraries that are used as the foundation for our generative AI that we have these days. Okay, it says here it's user friendly, it has simple APIs, and then the feedback it gives you in code is pretty clear if things aren't right. It says it provides modularity. We can fully configure modules that can be combined with few restrictions as possible. Part of that is because it's built on top of other libraries. So they're leveraging other libraries that came before, right? And I think that's clever. And what a lot of people do with this is it's easy to add your own modules to it. So in other words, if you come up with a bunch of functions that work with it, you can package it up, make it a module, and share it with others also. So people add to its capabilities. So if it's not doing something they need it to do, they just tweak it a little bit, create their own thing, and are ramping up the skills. And that's what they mean by being extensible. So another reason why it's very, very popular. PyTorch is another really important one. This was developed by Facebook and their research lab. It's built on Lua. Okay, so if you guys aren't familiar, Lua is another programming language. And Lua is often used for high-end scientific programming work and calculations. So I mean, that's a language that you can look up and learn. I mean, once you know how a couple languages, it doesn't take much to learn another. However, right, you can use it in Python, right? Because they have libraries that they've built now. So they've exported it from Lua, and now you can use it in Python, in a language called CUDA or C and C++. And it's also, notice that those last couple of words are designed to scale the production of building models, and overall flexibility. So this one is really good when you build really, really large things and you need to keep ramping it up, right? Which is, and that's Facebook's issue or problem or success. But yeah, so it came from that language. If you want to look up an interesting language, that is a pretty interesting one. But we do have libraries for Python. It gives us what we call tensor computations, which is in next bullet, multi-dimensional arrays, just like how NumPy can multiply and do dot multiplication with arrays. And because of the fact that it works like that, it runs really well on GPUs, right? So, and that's a big move right now in AI production too, is a lot of companies are using GPUs to run their algorithms. And I think that's just all so fascinating that they're doing it that way. I think I read an article really recently that NVIDIA either released or is close to releasing a regular like desktop CPU kind of built on their architecture, which is going to be a competitor to Intel and the ARM chips and the M chips from Apple, right? They're like their own like different kind of CPU. So it'd be interesting to see how well that stuff handles AI. I think it's kind of built for AI, if I understand it correctly. And they also have a package for PyTorch that builds graphs from tensors and automatically computes gradients. So it's kind of all built into that platform. So PyTorch, one of the things that it does, instead of like predefined graph structures that we just kind of work with, it gives us the ability to build stuff from scratch and change them even as they're running. So like you're watching your model run, and then you can go, maybe it would be a little better if I just tweaked it a little. Oh yeah, and you can do it. You don't have to stop it and restart it. And right, so it says that's very valuable when you don't know how much memory is going to be consumed or anything like that. So if you see that your model is consuming too much energy, maybe you can change it so it doesn't do as much. They use it in image detection, classification, natural language processing, and reinforcement learning. So PyTorch is used for those. Here's another one called Cafe. Cafe is one that came out of Berkeley, and it stands for Convolutional Architecture for Fast Feature Embedding, a mouthful. This one was written in C++, but it has a Python interface. So that means you can use the library in Python. And I know I said this during the Python class many times, but a lot of times the libraries that we have in Python that we use, like the math libraries, for example, a lot of that stuff was written in the C language or the C++ language a long time ago. And what they do is they make interpreters basically that take that code and allow it to work with Python, right? And it's kind of like an interface. And this is what they're talking about here. So it's written in C++, but you can use it with Python because they have an interface for it. Image detection and classification is its big thing. And they have a lot of pre-trained networks and models and weights that you can just utilize. You can just grab them as tools and apply to your problem and solve your problems pretty quickly. The different frameworks, the Zoo framework works really well with simple regression. Which is very important in the data world. Large scale visual classification, Siamese networks for image similarity, not necessarily exact, and then working with speech and robotics. You'll see a lot of people use this technology and borrow from it when we do academic research, when we're doing prototyping of different AIs or trying it in various environments like in industry. It does work well with GPU and CPU based acceleration. And so like if you were working with like a bank of NVIDIA graphics processors, this might be a tool you use because it's designed to take advantage of the architecture of those chips. All right. Here's another one, Deep Learning 4J, and developed by a bunch of different people. They wrote it in a collection of different languages, which is not unusual, actually, including Java, Scala, C++, C, CUDA, and whatever. It supports convolution networks, recurrent and long short-term memory as well. And once again, this is also designed to work on distributed computing platforms. That's where we take the workloads of our code and our machines or whatever and split it across multiple computers or CPUs or GPUs. So that has the capability to leverage those technologies, right? And so another reason why this one is popular. It does use a tensor library, which is called ND4J. And it gives you basically the ability to work with multi-dimensional arrays. And mind you, multi-dimensional arrays are actually called tensors. So that's why, we talk about that. And remember, an array is like a Python list, but when we're talking multi-dimensional, there's, lists of lists or lists of lists, or you can go down that rabbit hole. And look at the second bullet here. This is kind of interesting. It separates the process of loading up data and training algorithms into separate processes, which is not normal for a lot of the other libraries. And so like you can be loading up information as you're training your thing, not waiting for all the it's like, wait, I got to download it first and then I can run it. No, you can like download it and run it at the same time is kind of the point. It works really well with a lot of different data types. They say images, CSV files, plain text, but it really works with a lot of different things in deep learning. All right. Let's take a quick look at how this is helping all the Gen AI stuff happen. And I realize we're running out of time quickly, but we're also nearing the end of the slideshow. So fortunately, it says deep learning provides developers all the tools they need to build and train generative AI models. And so these libraries that are pre-built in these tools really are largely responsible for the rapid development of AI. So if somebody's already worked out some sort of capability in some library, like let's say voice recognition, well, that's going to save me the time of building the models, training them, making sure they're accurate, refining that, all that stuff, right? It's just there. You just grab the library, add it to your Python code, and leverage it. And in the process of doing that, you create new things, right? And you can start to combine, tools together, and they have a bunch of, like, as it says here, predefined model architectures, especially made for generative tests, transformers, variational encoders, general adversarial networks. These are all things we've talked about, right? The example they use is PyTorch's neural network modules make it simple for developers to define GAN model generators and discriminator parts, and without having to go through the rudimentary process of building it from scratch. This type of approach that we're talking about here is why AI has accelerated so much. When like DeepSeek came out a few months ago and everybody was freaked out by it because like the Chinese were able to build this high performing AI using open source code. What open source code are all these libraries that we're looking at? Just the way they're combining them and using the tools together, right? It's kind of like plug and playing with APIs, basically. Deep learning frameworks offer effective optimization models, right, for generative AI models, right? So like if we're going to try to do generative AI and we already have things optimized in a network or whatever, it really helps us to accelerate. Built-in functions for backpropagation, gradient computation, and loss functions. It says in order to change the model parameters during training, TensorFlow offers optimizers like Atom and SGD, right? So we can apply those. A lot of these also take advantage of the architecture of GPU chips, which is different than the architecture of CPU chips, right? So every thing, GPUs, of course, are built to process graphics. And if you think of what a graphics processor does, right, every pixel on your screen is repainted by the amount every second by the refresh rate of your screen. So if the refresh rate of your screen is 60 hertz, it's refreshing 60 times a second. And if you're like a gamer, or you have a high def monitor like mine, it might be 144 hertz, and every pixel is redrawn, and it's got to calculate vectors and matrices and 3D renditions and do that super, super fast. And regular processors don't necessarily do that as well, by the way. And the point of this is, right, because they're built to do graphics, they have like wider data paths and the ability to work with advanced computations in a different way. They handle big matrices efficiently and in parallel, which is essential. So like they have bigger data pathways going through those GPUs. It says by configuring the Keras framework, for example, to run on GPUs, developers can use GPU acceleration to speed up training. So if you have machines that are capable of doing that with the right GPUs, you can speed up your AI development. Okay, so yeah, another driver of today's revolution. Model deployment. It says deep learning frameworks have features that allow developed generative AI models to be exported and deployed to a variety of platforms and devices. So we are now running generative AI models on our phones, or maybe locally on our computers, where they're actually installed and running here. They enable developers to deploy gen models in real world settings, mobile apps, cloud services, with a lot of different deployment frameworks and libraries, and they can kind of mix all the services together. The example they have is TensorFlow offers TensorFlow serving, which makes it easier to deploy models for making predictions in a real world setting. If only they could have predicted all the Texas floods, right? All right. So they have some hands-on activities here, and they, we are at 3 minutes left, so we're not going to go through these. But I would highly suggest that if you guys have the time to download the data set, so you can click on the link here, and it will take you to the web page that they're showing on the screen. And this is a very ugly looking web page, but they have a bunch of different things that you can download. And notice that they have images, annotation, lists, different features. These are not small data sets, and I'm just putting that out there for you guys. And the data set is based around images of 120 breeds of dogs from around the world, built using images and annotation from ImageNet, and number of categories, number of images, and so it tells you all about it. And it's a very rich and deep data set. This is a visualization of some of the data just to give you an idea. But if you wanted to try that out, please feel free. We have a homework assignment, which is listed. And I'm just going to very, very quickly hit that while I think I have it open somewhere. Nope. Oh, here. Right. So the assignment on this one is to basically use this diabetes CSV file following the examples in this networks notebook. And first you want to look at the data, right? We'll build the neural network, right? Following the examples. We're just going to take what's there, feed it a different file, tweak a few things, and then we're going to visualize it and add regularization. And then I have some questions for you to think about, but if you follow the notebook, you will be fine. I am going to cap the video here, and I'm happy to kind of like dig into some of those files if you guys want a little bit of insight on it before you tackle it. I'm hoping to try to record either solution videos or example videos of how to work with this, but you guys see how little time we have during class with all the materials we're trying to cover. All right, this video will end here. and then I will hang out and talk with you guys if needed.